Hello, welcome back to another Python in Excel video. I have been re-watching this How Fast is Python in Excel video on YouTube. It was published about a year ago, and it draws some comparison with how you can use the Pixel add-in, which was developed by this guy, Tony, and Python in Excel. So things have come a long way since 12 months. And I wanted to just maybe redo the speed timing of the Python in Excel version of this code. Now, in this video, Tony creates some functions. You can see them here. He's created these functions to do this Black-Scholes option pricing, a call and a put function. He then decorates them with this Excel func decorator, and he calls or imports this module via Pixel and can then use it in the Excel file. Just to be absolutely clear, I think Pixel is a great add-in. It is very powerful, and it's been around for a while. It's got a lot of good things about it. My video is not to say Pixel is slow or Pixel is no good or this or that or whatever. It's more to show that the method used to time Python in Excel in this video is perhaps not ideal, and there is a better way to use the same technology to get better speeds. And I'm going to show you how to do that. So in the video, Tony creates these functions using the Pixel add-in, and then he calculates them against this data. There's 1,000 rows of data here. He calculates the call and put functions, one function call per cell. Now that's quite normal when you've got a user-defined function. But these days we have dynamic arrays, so it would probably be better to map the function over the array or use by row over the array or something like that, rather than one function call per cell. So in addition to that, he creates a cell in J1 of the spreadsheet and defines the functions. This is how you do it in Python and Excel. You define the functions, say in row 1 or in column 1, and then any cell that is after that on the same row or in a row below can use those functions. So he's defined them in J1, and then he moves on to call it from, to begin with, F2, and then copies it down, one Python cell per row. And this is essentially the issue here. One Python cell per row means one round trip to the Azure container per cell per row, one per function per row. So that's a lot of round trips to the container. It is a much more effective strategy to pull all of the data into a data frame and then apply the function to the data frame. And that's what I'm going to show you now. So over in Excel, I took this screenshot from the video directly, and then I used data from picture to basically extract the numbers and the data from that screenshot into this range. I've also taken a screenshot of this code because we'll be replicating this code in Python and Excel. But we're going to make use of Copilot because I want you to see that Copilot is actually very competent with Python tasks. So I've got this range of sample data, but it's really only 19 rows, and I want 1,000 rows of data like this. So I'm going to open Copilot and ask for its help. I want to generate 1,000 rows of data similar to the data on the sample sheet. Use Python to do this. The domain of each variable must be within the bounds of the domain in the sample data. And this is just to say that I don't want it to create any zeros really or massive numbers in any of these variables, but more that I just want some fake data that is kind of like what we can see on the screen. So I've told it specifically to use Python to do this. If you don't do that, you may end up with formulas. That's fine as well, but I want Python because I want to show you what it does. Okay, this is a good sign. I can use advanced analysis for that. Here's what I'll do, and so on and so forth. When we click start, it will do the work. It creates a new sheet called analysis 1 and it loads the data and then it creates a preview. I will show you all of this in just a moment. And the next thing it's doing is actually generating the code to generate 1000 rows. And then it will show a preview of that and then it will wrap it up and it will be finished. And then we can talk about it. Okay. So the first thing it has done is created this sheet, analysis 1, and then it's created some headers and it's noted that it was code generated by Copilot. So in the first, in cell A5, we've got a Python cell and it has created a data frame, sample A1E20DF, and it's used the Excel method to get the data from the sample sheet into a data frame. Now, interestingly, below it's created this preview, and the preview is not a Python cell, but because we are returning a Python object in cell A5, we can use this dot array preview to see a preview of the data returned in that object, which is really useful because it means that this code that's generating, or this formula that's generating this array in cell A8, this spill array, is not a Python cell, so it's not going to Azure. It's just referring to the data that was returned previously. So that is super useful. The next thing is the code to generate 1000 rows. If we just expand this, you can see there's more code there. So what I'm going to do is open the Python editor. We go to the formulas tab of the ribbon, click editor and make it a bit wider because it's easier to see if you do that. I will expand this and hold down Control and roll the mouse wheel. And you can see it's done some imports. These are actually not necessary because Python and Excel imports these by default when it initializes. However, doing this does not cost you anything because it already recognizes that they're imported, so it really does nothing. It's created the min of the values and the max of the values and then used those to define the domain of the variables in the new data frame. So new data, and it's creating 1000 rows for each of these series, SKT, row, and sigma. And you can see again, it's using the if error a22.array preview. If that's an error, then return the Python string from that object. But it's not an error. It's returned the head 5 rows and the tail 5 rows from that data frame. And you can see that there are 1000 rows because the first index is 0 and the last index is 999. So I'm going to rename this sheet to data via Copilot. The next thing we need is some code to generate those functions, some code for those functions that we are going to use to test against this data. Remember, I created this here. I took this screenshot from the video because, you know, I'm actually not an expert on option pricing, believe it or not. It's probably quite easy to believe. But I wanted to check the code that Copilot is going to generate against this because Tony is an expert in this kind of stuff. And if the code that Copilot creates is the same as this, we'll treat it as good. So let me go to Copilot. And next, I need to define 2 Python functions for Black-Scholes option pricing. 1 for call and 1 for put. Call them BS call, BS put. So we'll see if it can generate it correctly. It's gone back to the data via Copilot sheet and it's working on it. Oh, it's created a new cell. It has summarized my request into a header for that cell. And let's see what we did. Here's what I inserted. Okay, this is the code that it inserted, but let's use the editor to look at it. Python editor is here. And we want to go to cell A39 and expand it. Now what I want to do is grab the screenshot from the other sheet and put it here so we can compare them. Okay, so BS call defines D1, D2, and then it returns the call price. D1 is looking at the code, this is half of sigma squared, which is also defined similarly there. And this is doing np.square root. And this one is assigning norm.cdf to n and calling it twice in the return statement. In the Copilot code, it's just using it in the definition of call price and then returning call price. So this function here is the same as this function here. And just scanning quickly BS put, it's the same principle with defining the half the square of sigma, and is defining put price and then returning that. And similarly here, it's returning the same expression. So in summary, I'm confident that the code generated by Copilot is correct for this test, because I've tested it against the code from an expert. So let me take that away, put it back here in case I need it later. And it has defined that in cell A39 on the data via Copilot sheet and put a heading above it describing what it is. And I think by default, it's creating a preview for every cell that it creates. So even though that's just defining functions, it's still created a preview. I'm not sure that's really necessary. I'm just going to get rid of it because I pressed insert and I meant to press delete. Get rid of it. I don't need it. Okay, so the next thing to do is test. We're going to test how fast this thing is. I'm going to create a new sheet and I'm going to call it test. And the first thing I'm going to do here is create a Python cell, which is going to be the data frame that was created with the synthetic data, which is just called new data. And I'm going to save that. By default, it outputs the object. I actually want it to output the spilled array. So there's the data. The next thing I want to do is I want to apply the call function against this data frame. So in the video on YouTube, what Tony did was use the Excel method to pull in each of these 5 columns. That is one way you can do it. It's kind of not the best way that you can do it. So I'm going to show you a better way now. I'm going to create a new Python cell and I am going to say new data and apply. And what I'm going to apply is to each row, I'm going to say BS call, and I will explain this in just a moment. Equals 1. And we want that to output as Excel values. And I hit save. I could just do Control Enter as well. And you can see that it has spilled the array actually very, very quickly. Let me explain the code. First of all, this is the synthetic data of 1,000 rows. We can use apply if we want to apply a function to every row or every column in a data frame. Within there, we need to define a function, or we can use a callback function, or we can define a lambda function. In this case, I'm using axis equals 1 to tell it that I want to apply the function once for each row. If I took this away or said axis equals 0, it would try to apply the function once for each column, which is not what I want. So by putting axis equals 1, the parameter to this lambda function is a row. Therefore, I can put it here. And if I wrap it in tuple, it creates a tuple that contains the 5 elements in each row. And this little asterisk here, when placed in front of a tuple, does some kind of magic. It's called argument unpacking. And it takes the 5 elements of that tuple and it unpacks them into the 5 parameters of the BS call function. So in this way, I don't need to assign S to a variable called S and K to a variable called K and so on very, very tediously. I can just unpack the row into the function and execute it. You saw how fast it was, but let's time it. I can use an IPython magic command called timeit to do that. And if you put %timeit at the beginning of a Python cell in the same way as if you would in a Jupyter notebook, it will time how long it takes to execute the code in that cell only. So it will not take into consideration any of the other Python cells in the workbook. It will just time that cell. So let's press Control Enter and see what it comes up with. It takes a bit of time because it is not just executing it once, it's doing it several times, so it can take an average of the execution times and give us a somewhat accurate response. So we just sit, wait patiently, and you can see that the result is that this code takes about 161 microseconds, give or take 17.2 microseconds. So I'm going to copy that so that we can keep a note of it and paste it in here where it's tiny. Make it much bigger, maybe 10, 11, 12, wrap text, make that a bit wider, double click here. And so that's the timing for that. I'm now going to remove this by pressing Control X, and I'm going to execute that again just to spill the results there. Let's do the same thing, press equals PY, do the same thing with, don't do it in the cell. Use the Python editor because that's much easier. Okay, so we're going to do the same thing with the other function, time it, and put new data.apply. I could copy it from above, but I've already committed to doing it this way. Row bs put, and we're going to do star tuple row, and then axis equals 1. And when I press Control Enter, it will do that timing command on the bs put function for 1,000 rows. Suspense is killing me. Okay, so that came back with 155 milliseconds, give or take 4.94 milliseconds per loop. Pretty fast. If you then consider, let's make this the same as that. Okay, let's just do that and then do this and then change this, just get rid of that. And change this to Excel value and click save. If you then consider that we have run over 1,000 rows, 2 functions, without a lot of messing around with variables and assigning the Excel method, we have executed all of that in about 315 milliseconds, give or take 20 milliseconds. So let's say less than 350 milliseconds for 1,000 rows, 2 functions of somewhat simple, but moderately, let's say moderately complex calculations. So that's what you should do if you have this kind of challenge in Python and Excel. If you want to do some finance calculations, if you want to do engineering calculations, pull all the data into a data frame, define your function elsewhere, apply the function to the data frame in this way, row by row, using axis equals 1. There are faster ways to do it. This is probably sufficient for most people's needs. So hopping back over to the video, let's see, I should have written down the exact timing. You can see that Pixel, he has calculated the entire workbook in 140 milliseconds. So that is still really, really fast. It is really fast. It's faster than the test that I just did, in fact. If we look at the test on Python and Excel, where he's defined separate variables using the Excel method and then passed those into the function, but he's done one call per cell, it actually doesn't finish. And my view is that it doesn't finish because it's one call per cell. This is not a failing of the technology. It is a misunderstanding of the best way to do it. So please use a data frame. Apply your function over the data frame. Don't try and do it row by row, calculation by calculation. That is an inefficient way of working. So again, I just want to reiterate, this is not about saying bad things about Pixel. Pixel is super fast. It's really useful. It requires a bit more management to get set up. However, Python and Excel is very fast. It is totally integrated into Excel. You do not have to manage the environment. You don't have to worry about security of the packages, because they are all provided by Anaconda, and Anaconda are the people for secure package distribution. That is just a fact. That's why Microsoft chose Anaconda. You don't have to worry about any of that. You just open Excel and you get started. That is it. Thanks for watching. Have a great day.